All right, part two. And it's worth splitting these things up because there's a massive difference here. And the most common mistake is not realizing that there's a difference here. What I have given now is a graph of the derivative. And so remember, what that means is the y values here. So for example, at this point here, negative 1 comma 5, that means there's some original function that when x is negative 1 has a tangent line, and that tangent line has a slope equal to 5. And this graph just graphs the slopes of all those tangent lines as its own function, right? It's a lot to work with. It's a lot to wrap your head around. So once again, the chart is your friend. If you can write the chart down, you can reason these things out, and it helps kind of be training wheels as you're developing your intuition. So, for example, f of x increasing. F of x is increasing. We're going to start off light when the derivative is positive. We've done a whole unit on this. Remember, you just have to make the realization that what we're looking for here is when the derivative, the slope of the tangent line, is a positive number. That's going to be true from negative 2 to 1, and then also true from 3 to infinity. And the reason here, straightforward, because the derivative is positive, or because the derivative is greater than 0. Going the other way, the only times when the original function, f of x, is decreasing is when the derivative is negative. So that's going to be from negative infinity to negative 2, and also that little dip there from 1 to 3, likewise because the derivative here is less than 0. So increasing and decreasing leads directly into these next questions. All a local min is, it's when your original function was decreasing and is now increasing. But what that means for this function is, where does the derivative switch from negative to positive, right? Negative to positive here. And so that's going to happen at negative 2 and at 3. Because if the derivative is switching from negative to positive, the slopes of the tangent lines are, and that's how you make a local maximum. So that's going to happen at x equals negative 2 and x equals 3. And what we would say here usually is f prime of x switches negative to positive. And we've covered this before, so this part should be mostly review. Local maximum would be when the derivative, the slope of the tangent line, was positive, then is 0, and then is negative. So that's going to be at x is equal to 1. I'm going to erase this other red dot so it doesn't get confusing. And the reason there, f prime of x switches the other way. The derivative was positive. The original function was increasing. Now the derivative is negative, was decreased, and now is decreasing. So the tricky ones, the ones we're adding here, are concave up and concave down. And so this is where, especially when you're getting started, the chart can be helpful. Concave up, in the original function, we are looking for where the derivative is increasing. So we are looking for these values here, where the derivative is on its way up. And if you just kind of, this takes a while, if you kind of make your hand motions a negatively sloped tangent line, and then a little bit closer to flat, and then 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 closer to flat, what you'd find is you're making this shape with your hand. You're making the shape that looks like that left-hand side of the cup if you were to make that shape. And so those are going to be the areas where the function is concave, where the original function is concave up. And so that's going to happen, not at, but on the intervals where f prime is increasing. So now it's from negative infinity all the way to negative 1. And finally, the second one from 2 to infinity. Because in both of these locations, the derivative is increasing, which is the definition of concave up. And so we're going to say here, f prime of x is increasing. Likewise, concave down is that section in between, this section right here, between the max and the min. And so that's going to happen at or on negative 1 to 2. And the reason here, f prime of x is decreasing. Finally, at an inflection point, well, that's the definition of an inflection point, is when these things change. So remember here, this is especially where things get tricky. I'm not asking when f prime is at an inflection point. I'm asking when f is at an inflection point. And f is at an inflection point where we hand over from f prime increasing to decreasing, or vice versa. Again, we're here and we're looking at what's happening to f prime. And so that's going to happen at x equals -1, x equals 2. And the reason is because f prime of x switches, and I would say here, increasing to decreasing, or vice versa, or the other way around. Now, once again, we can make the exact same conclusions about the second derivative. The second derivative, if you are at an inflection point, that means the second derivative is 0. So this is the exact same answer at x equals -1, x equals 2, and the exact same thing, because f prime of x switches increasing to decreasing, the exact same thing. And the second derivative being positive is the exact same thing as saying the original function is concave up. So it's the exact same answer from -infinity to -1, 2 to infinity. And the reason here is because f prime of x is increasing versus for concave down, that is the exact same thing as saying the second derivative is negative. That is what concave down means. It literally means having a negative second derivative, and that means that the first derivative is decreasing. Again, very tricky when you're first getting started. Use the chart, take a deep breath, take it slow. We have one last one to do. We're going to look at how do we make this same analysis. Notice there's a lot less to do here, but for graphs of the second derivative. And so we're going to do graphs of the second derivative here, and there's really not as much we can say. If we have a second derivative, well, what are some of the things we can say? We can say when f of x is concave up or concave down. And so if we look at what that's saying, when you have a graph of the second derivative, that's referring to the sign of the second derivative. Just what's happening to the second derivative, or sorry, where is the second derivative? When is it positive? It's positive. Oh, and then it keeps going positive. So it's actually from 0 to infinity. On all that entire interval, the second derivative is greater than 0. And so what we have here is a function that is concave up versus an original function is concave down when its second derivative, which is what this is negative. And so that's going to be from -infinity to 0. And what we're going to have here is the second derivative is less than 0. The inflection point is where we change concavities, right? That is the literal definition of an inflection point, where you change concavities, and so that's going to be at 0. And so just like we would for a first derivative justification, we're going to say here f double prime switches signs, okay? Now, probably the trickiest one here of all of these is making conclusions about the first derivative based on the second derivative. And so we really, when we're getting started, just want to use the chart here. The first derivative is increasing, so I looked that up on the chart, okay? But I have a graph of the second derivative, so all I'm looking for here is when the second derivative is positive. Oh, okay, yeah, that means the exact same thing. That is what concave up means. It means the slopes are increasing. So this is the same answer as when f of x is concave up. It's because the second derivative of x is greater than 0. And likewise, that is also what the first derivative decreasing means. It means the second derivative is negative. And so what we have there is -infinity to 0 because the second derivative is less than 0. Now, finally, the weirdest one here, the one that kind of is a mind bender here for a lot of people, is when the first derivative is at a local min or a max. Again, this is some unpictured first derivative, but you have to make the connection that when I say a local min, that means a function that was on its way down and is now on its way up. And so what you're looking for is when the first derivative switches from decreasing to increasing, which means the second derivative switches from negative to positive. And that does happen here. That is what happens at this inflection point. So this is at x equals 0, and the reason is the second derivative switches from negative to positive. And if the second derivative switches from negative to positive, the first derivative switches from decreasing to increasing, that is the definition of a local minimum. Now, when we go look for a local max, we're looking for the opposite. We're looking for positive to negative. That never happens. There's no location where the second derivative switches from positive to negative. And so I would say that f double prime of x never switches positive to negative. And that's all.